Now, when you think about scope, think about access. For example, you can have a mechanic that's going to repair a car engine, and we know that objects contain objects. They have scopes. You can't just open up a car engine and then pull out a piston, for example. You need to take the engine to pieces. You need to take the engine blockhead off, and you need to dismantle the entire engine block. So we understand that there is scope. You can't just lift the bonnet up and pull out a piston. There is ways in which you can access objects nested inside of other objects. And that is exactly what scopes are. Whether it be a standard object or a callable object, these are scopes. They have their own access level. They have their own defined perimeter, if you will. And some have greater access and some have more limited access depending on where that callable object is and where that object resides. And that's all that scope means. And just like objects in our program, you know they have scopes. You know you can't just type in, for example, engine, and then we want to pull out the very first piston like so. You couldn't do that. You're just going to get undefined. And the reason why you're going to get undefined is because it's not defined. The pistons are not defined in this scope that you can see. This starting and ending braces in there, in that scope, pistons are not defined. And so we don't have that access to that array yet. But what we need to do is we need to take off that head gasket, or you need to take off the engine block and so forth. I'm not a mechanic, so do forgive me on this one. But what I need to do is I need to say, right, there's the engine, there's the overall engine. Now we need to take off the head gasket, for example, and then we need access to the pots. And in the pots, there is an array right here, and then we can access one of the pistons in our engine, just like a mechanic knows that he needs to go through multiple objects to get the object that he needs to fix and repair. And you, as the programmer, are that mechanic. You're the mechanic that needs to be able to know how to access your objects and how to access them individually, one by one, and then you can pull the data out. That is called scope. It has an access level. Now, don't forget that functions are also called callable objects. They have their own scope. They have their own execution context. If you have a look here, it is those braces again, and you can tell those braces, they have scope. That's why our IDE, our editor right here, can actually collapse the brackets because that is a scope. Like so. So you go to engine, then you go to head gasket, then you go to pots, and then you can access one of these elements. So that is all to do with scope. And functions have scope. You'll notice we have function, run expression, and then what we have is we have a variable called a is equal to 10, and you also have an embedded callable object called add. And this returns an expression. It returns a, which is defined outside of this callable object scope, a plus 90. So I've created the variable in this function, run expression, but in this embedded function, I'm actually calling up that symbol called a. And we're going to say add 90, and we run that add callable object, and it will return 100. A is 10, 10 plus 90 is 100. That will then be returned when we execute this function. So let's go ahead, and what I want to do is actually run the function. So I'm going to say run expression, then we need the parentheses to invoke it, and when you do, you get the value 100. So this is what we have scopes for. Now, let's say I created variable b. So I created var b is equal to 90, and then I say a plus b. So that should return the same thing. If I save and refresh and we run it, that's fine. Instead of the old equation, I'm just storing the number 90 in the b symbol. So what actually happens now? If you try to do this on a regular object, you wouldn't be able to do this. For example, if you said engine, then you went into head gasket, then you went into pots, and then let's say you wanted to go back out and say, right, I want to target maker, like so. If you actually try to run this, you would find it would return undefined. In other words, this memory pointer doesn't actually exist within this scope, because that's the scope we're targeting, which is this array, and then it's trying to find the symbol name maker inside of this array, and it can't find it. We've only got 0 and 1. So you can't do this with regular objects, but callable objects are different. Callable objects go on to what is called an execution stack. And what do we mean by this? Well, if you think about it, you have a stack of papers, for example, and each paper could be a function, a list of instructions to run, and we stack these papers up ready to be run. And what's stacked on here is the execution context. So first of all, you have the run expression execution context, and then also you have another execution context, which is called add. And this execution context is placed on the stack also. Now, what's happening with these execution contexts? Well, the run expression is first of all being executed, and it creates the symbol A in the symbols table. After we finish the run expression execution context, we have the add execution context. But what it does is it doesn't just automatically delete something out of memory. It says, can potentially another callable object access the symbol A? And the answer is, yes, it can. So it leaves it in memory. This is called a closure. It encloses and it encapsulates and it keeps together all of the symbols that have a reference to them or could have a potential reference to them. And also, don't forget, the add execution context is going to create the symbol B as well. And then what happens is we say return A plus B, which is 100. So after all the execution is finished, we have 100 returned. Now, when we're finished, there is something called garbage collection. In other words, can any other part of our application access those symbols after we've finished executing? No, it can't. There is no other part of my application. If I try to access, for example, the symbol A down here, or I've already run the function here, can I access A? No, you can't. And you can't access B either. So what's the point in leaving or wasting memory by storing these values and keeping these memory pointers? Because no longer can our application access it. Only these callable objects, only what was in the scope of these callable objects could access potentially one of those symbols. So now that we're finished with our execution, it simply deletes those symbols out of memory. That is called garbage collection. It gets rid of waste symbols or symbols that we no longer need. Now also, let's say that we run the add function and then we try to access in the outer scope, in the run expression scope, the variable B. Will this work based on what we have just seen? The answer is no. So let's go ahead and delete that and just hit refresh. And then what I'd like to do is say run expression. Now when I say run expression, it'll say, sorry, B is not defined. So what happened? Well, again, we have this execution context and it runs this execution context first. It does not run the add execution context after. So what happens is it created a symbol called A, which is equal to 10. There's nothing wrong with that. But when it was invoked, we invoked the add callable execution context, but it just added it to the stack, one below. So all we have is a symbols table that has the A symbol. B has not been created. So when you invoke a function, it doesn't mean that it's going to invoke right there, dead center, and that's where it's going to invoke. No, it's just pushing it onto the stack of papers, and each paper is a list of instructions. And it's not run those list of instructions yet. It's not run the add list of instructions. So that function hasn't been run and the symbol B hasn't been created. And therefore we get this error. So it runs this execution context, then it runs the add execution context. That is very important to remember. Just because you have it invoked here does not mean that it immediately invokes the subroutine right then and there. It adds it to the stack and then it goes down the stack, and you can have functions inside of functions, just like objects inside of objects, callable objects inside of callable objects. And when you invoke each one, you are in fact adding to the stack. So for example, if I had add and add, then that would actually add the callable object twice onto the stack. And we can have the parameter now, B, and then you can set one to 90 and the other one to 20, and you get different results out in the console. And we can just log this out in the console. So I can say console.log, log this out. and hit refresh, run expression, we get 130. So it created the outer execution context and it said, right, we need to run these system instructions. Right, we want var a equals 10. It created that symbol. Then it noticed that we invoked the add subroutine twice. And as we invoked it twice, one with the value of 90 and the other one with the value of 20, it adds those into the stack with the argument values. And that's what's happening here. It's called the execution stack. And yes, you can have the same function repeated over and over and over again on that execution stack, or what it is known as is the main thread. And you can think about a thread of string with beads on it, and each bead is your function. And we just run each function, we throw each bead off the thread and we get what's returned. And we also have a temporary symbols table for the temporary execution context. And when we encapsulate this main thread with this temporary symbols table, this temporary database that stores symbols, it is called the outer execution environment. That is this environment. It's a temporary environment in which our functions and those symbols which those functions have created just for the process of those functions, and that is this environment in which we're executing these lists of instructions here, and then it's cleared out. It's only a temporary space for execution to happen in our JavaScript program. So, functions are callable objects. Callable objects have scope, just like regular objects, and you can have objects embedded in objects. But callable objects are special in the fact that we have this temporary symbols table, and the language feature is called a closure, where any sort of symbol that's created inside of our execution stack, as long as there is another callable object in there, still in the execution stack, it keeps the symbol, it encloses everything together, and it keeps those symbols whilst we are executing all those instructions on the execution stack or the main thread. Then once all of it's been executed, it returns the final values and it does all of its operations. It then clears out the symbols that we can no longer reference in our program. Once we've executed these list of instructions, we've done what we need to do with these instructions get thrown in the bin. Our instructions are in the bin, and now we get garbage collection as well that deletes out these symbols so we're not wasting memory. And that is also garbage collection, and garbage collection is a big part of memory management so that we don't end up filling up all of the user's RAM and crashing the browser and being very, very inefficient in storage. And JavaScript manages that automatically for you.